Riemann Hypothesis. Prime numbers like 2, 3, 5, 7, 11 seem random. But are they? Bernhard Riemann believed there is a hidden rhythm behind where primes appear, like a cosmic heartbeat on the number line. His Riemann hypothesis suggests that all the key points of this rhythm lie along a perfect line in the world of complex numbers. If this is true, it would reveal the deepest pattern behind primes, which are the foundation of online security and modern cryptography. Mathematicians have checked billions of cases, and all of them agree so far, but proving it for all numbers, from here to infinity, is still an unsolved challenge. Hodge Conjecture. Think about shapes far beyond what we can see, strange twisting surfaces in many dimensions. The Hodge Conjecture asks, can we describe these shapes using simpler, more familiar pieces, like breaking a machine down into basic parts? For some shapes, the answer is yes. For others, we do not yet know. Solving this problem would open new doors in geometry and physics, helping us understand the structure of space itself. Yang-Mills and the mass gap. This problem is not just about math. It is part of modern physics. The Yang-Mills theory explains how tiny particles interact. But one thing is missing: the mass gap. It asks why some particles that should have no mass actually do. We see the theory working in experiments like particle colliders. But no one has proved why this mass gap exists from first principles. A proof would be like finding a missing page in the universe's instruction book, Euler's Sum of Powers. In the 1700s, Leonhard Euler guessed that you could not add a few numbers raised to the same power and get another number of that same power. For a long time, everyone believed him until counterexamples were found. Now, the mystery is to understand when these kinds of equations have solutions and how these rare number combinations appear. Even today, arithmetic still hides surprises. P versus NP. Imagine solving a huge puzzle that takes days, but checking the finished puzzle only takes seconds. This is the idea behind P versus NP. Some problems are easy to solve, P. Others are hard to solve, but easy to check once solved, NP. The big question is, are these two types of problems really different? If every problem that is easy to check could also be made easy to solve, it would change code breaking, medicine, and artificial intelligence. But if they are not the same, some problems will always remain hard, no matter how powerful our computers get. Goldbach's Conjecture. Take any even number, 4, 6, 10, even a million. Can it always be written as the sum of two primes? It seems so. Mathematicians have tested it for incredibly large numbers, and it always works. But no one has ever proved it works for all even numbers. It is a riddle so simple you can explain it to a child, and yet no one has fully solved it. Collatz Conjecture. Pick any number. If it's even, divide it by 2. If it's odd, multiply it by 3 and add 1. Repeat this process again and again. No matter where you start, 6, 19, or even 10 million, you always seem to end up at 1. It feels like a simple game, but proving it works for every number is still one of the hardest problems in mathematics. There might be some number out there that breaks the pattern, or maybe none at all.